Alright, time for another draftphysics.com, debatephysics.com. But no real point in having websites on the internet because Google won't index them, so they really don't exist. So, just a fact, facts. They're kind of an important. So you could do probably lots of experiments and prove that Google's a shit engine, but no one's going to do those either. Oh, it's just such a sad, tragic world we live in. Far short of the civilization we should have. But, morons, demand moronic stuff. And, so it just is a reflection of the people in the civilization. So anyway, something called an ambigrabby, says no energy exists, in quotes, whatever that means. A qualified exists? I don't know. What does that even mean? So he's just going to tell me his Jesus story. Jesus is the Son of God, and God is the creator of the universe. And he's going to tell me a story with no evidence. And it's just going to be his own little story. Energy just a state you are in. So, state. So like a condition. It's a condition you have, except you don't have to conserve it, I guess, because then it wouldn't be a shared condition or an exchange condition. What the fuck? So the condition is indistinguishable from all other conditions. So it's a state you're in, but it's no different than every other state. So it's the same state. Fuck. Too ridiculous. When there's a force that is trying to pull you, so obviously there is no pulling force. So you can, go through all the examples where you never pull anything anywhere. You're always pushing it. Doorknobs, for example. You're pushing on the back of the doorknob. That means that if you let it, you will be moved. Again, says you. So there's no such thing as a pulling force. There's only the, relative absence of pushes in the universe. So if you can cause there to be a lack of push in one direction, the push in the other direction will take care of everything. So if you had a tank of fuel, and there's fuel trying to push on all the sides, and then you let some of the fuel that's going this way out. You put a little hole in the tank on this side. Well, then you'll end up going that way because you'll still have all the pushers going this way, but you'll be missing some of the ones that were going this way. Yeah, it's that simple. But, go ahead. Tell your Jesus theory instead. So much more fun. All right, we call this state having energy. I don't know who the we is, What the state is you have no evidence and you're telling fables that are preposterously silly because they don't make any sense. They don't have any mechanical moving parts. They're not physical. It's not physics. It's a fucking religion. All right. If the force is gravity, well, at least you're conceding it's a force. A force of what? Yeah, well, come on. Then you are said to have gravitational potential energy, which is just baby talk because there is no such thing as a potential energy. So again, if I have a boat on the side of the Mississippi River just sitting there minding its own business, it doesn't have any potential energy. It's not in any kind of condition. It's just a boat, and it could be sitting in any state, anywhere. All right, it's not doing anything. It doesn't have any potential. And what I have to do is put it in an active stream to make it go. So it didn't have anything. The stream has potential in the sense that the stream is an active source of energy and you can stick your finger in it and collect some of the energy. All right, if it is a spring, so whatever this is, so if it is a spring, which it isn't, that it is the atom's repulsion that the force, what? This isn't even a sentence of some kind. If the force is gravity, then you are said to have gravitational potential energy. If it is a spring, that it is the atom's repulsion that is the force. So obviously it's not the atom's repulsion, it's the electrons' repulsions on, electrons on the outside of the atoms. And what's that repulsion from? Well, what's the cause of it? But no. And we call it elastic energy. Well, you can call it anything you want, okay? It's just plainly stored pressure. So you've applied a pushing force, you've pushed electrons into electrons, and now they're going to push on each other and restore the previous equilibrium. But fuck you. I mean, you explained, this is such baby talk. You can't do any better than this mush. Ugh, I say so. Ugh, crap. Alright, then the channel 321 jackass, and we'll call him that. Alright, so the first question he asked was simple enough, right? So let me draw this out. And I answered the question. Okay, no big deal. What do you say will happen? So he didn't say anything about equal masses or any of that crap. And I even pointed out this is exactly the Professor Lewin experiment, where Professor Lewin says the magical phrase, nature can deal with kinetic energy one way or the other, but nature can't finagle momentum. And by finagle, he means make it non-conservative. Okay, so the simple thing is you have a spring, okay, and you're going to put a mass on each side of the spring. And so this is all he described, okay, and the simple experiment is that the total momentum, that is the amount of motion you're going to get out of this spring, is going to be the same, and it's going to be proportionally the same. So if they're one mass and one mass, I can expect the same velocity. Half the velocity goes this way, and half the velocity goes this way, and we conserve the momentum. Half the energy pushes this way, half the energy pushes that way. Okay. And now if I start to make this side heavier, that is if I just put a 2 mass here, so this is the exact experiment that he made the statement regarding. So I have a 1 mass and a 2 mass. Well, what I'm going to get, okay, is I'm going to get, the momentum's going to be conserved in the sense that both sides are going to get the same momentum. So obviously this is going to be going 1/2 the speed of this over here. So this is going 1/3 the speed, and this is going to go, no, the other way around. 2/3 here and 1/3 here. Okay, the velocity. No, it's still wrong. Still wrong. Okay. See, as soon as you start messing with velocities, you do make it confusing. This will go 1/2 of this one's velocity. So whatever this velocity is, this will be going 1/2 that velocity, to make it simple. All right, and the total momentum, that is the total velocities you're going to get, is going to be the same. So essentially it's saying this is going to go with 1/2. Okay, so it's going to get half the momentum, which is the same as it got over here. All right, so it's going to be leaving with the same velocity as it left here. And this is going to go 1/2 that velocity because of the bigger, heavier mass. But you're going to have the same momentum. So the argument would be the same for a 3 mass or a 4 mass. So that was his original question. So that's all he's doing, is asking his original question again. Okay, I mean, I thought he was talking about moving into springs and how things bounce off. So again, you could expect half the momentum goes this way, so the same exact velocities here. And that did come out in the experiment. If you watch the Lewin experiment, these two velocities were very similar. Now, I didn't use the same exact spring compression, so you didn't get exactly the same velocity, but it's close. All right, and this one will go away with 1/3. Okay, because it's consuming, a larger percentage of. I mean, it's being pushed with 1/2 the same force applied to a much heavier object gets you a much slower velocity. And you would assume it just continues that way until you get to that magical point where friction is going to start. entering the issue. That is, the static friction of the object is going to start increasing. Okay, so you're going to start consuming the spring's energy, just overcoming the static friction created by how heavy the object is. So you still won't get much more this way, and it's not until you make it rock solid, all right, the spring doesn't apply any waste to any kind of friction because it's basically just stuck to the ground. And then the spring will push the object with more velocity, okay, velocity plus, because none of the spring's energy is being applied to this direction. And instead, the spring's center of mass is moving this way. So the spring's center of mass moves in the direction of the push, and so you'll get more velocity because you've basically created the circumstance, sorry about that, where now the spring doesn't equally push in both directions. The spring itself has to move because it can't push this direction. So the spring itself moves in this direction and expands in that direction. So you get a higher velocity. Yeah, so that's the maximum velocity. Yes, if you push against something that doesn't move, you'll get more velocity than if you push against something that does move. And the trick is you're trying to push on things that have a minimum amount of friction, but obviously there's a point where you have a maximum amount of static friction where you will actually just consume the energy as not motion, but trying to break the friction with the surface. Alright, so did I explain that adequately? Now I'll pause and just see if there's a huge enough error where I have to say, oh fuck, I really did mess that up. I don't think it's catastrophically broken, but anyway. Alright, so I just want to make the distinction between these are two critical, they look a lot alike, these experiments, but they're not the same thing, right? So there's one experiment, the spring is in a place and you have two mobile masses. So the masses can move and the spring theoretically doesn't go anywhere. And the other case is that the objects have motion and the spring, say, is attached to one of the objects. All right, and now you're going to be basically pushing into the spring and moving objects. So the spring is going to be mobile. All right, and so you're coming in with energy, say with one object, or both objects have energy. And those are two different experiments. And so in this specific case of an experiment where the spring is compressed not by the energy of the objects, but you can pre-compress it, all right, and then you release it, okay, yes, this if this is always a one mass on this side, it will always get the same velocity until you make this side unmovable. So until this side's unmovable, you get the same velocity this way, and the thing you're making heavier, gets less and less and less velocity, indicating it's still getting 50%. Okay, it's 50-50. 50% of the momentum goes in each direction, always. All right, until the static friction starts eating, okay, this 50%. So you'll start to get very little motion in this direction because the friction is going to start consuming the energy of the spring, a big percentage of it. So you won't get a proportional indication. You won't get linear motion that's equal to your 50%. And eventually when it stops, then you'll move the whole spring in one direction. You'll move the center of mass of the spring in the same direction and add a little bit of extra energy. All right, in this other case is other things moving. So that's the case I explained because I thought, well, he's asking a different question. So I thought the different question required a different answer about what happens when you move things. And when you move things, it's going to matter because now whatever thing has the most momentum is going to control the direction of the motion, and it is going to move the spring with it, and it is going to be applying a pressure before it's loaded the spring. So the spring will never get completely compressed. So you're never going to load the spring with all the energy. So the spring obviously won't have all the energy, so therefore it can't expand evenly with all the energy because it never has all the energy in it. That should be enough of a clarification. All right, so to the comment. All right, so he said that really didn't answer my question. Okay, so I say it did because his first question I had already answered. But maybe my question was unclear. Yes, I'll try again. Okay. If we use a compressed spring to launch two objects, which was the first question, A and B, in opposite directions, does the mass of B affect the velocity gained by A? Theoretically, no, until you get to the point where the mass is great enough that the pushing force can't really apply any action to the object because it has to use so much energy to break the friction. And once the object, like an anvil, is unmovable, then you're going to get a complete reflection of all the energy. All right, if you say it does, okay, so the mass of V does not. So I'm saying clearly it does not. So here we go. In opposite directions, does the mass of B affect the velocity gained by A? So theoretically, no, until you get to a non-moving mass, a mass that can't be moved by the amount of energy you're applying. All right, if you say it does, which is true, says you, then that means the same spring compression can lead to different amounts of momentum depending on the mass of B. And I'm obviously disputing that. You can't create different amounts of momentum. The spring only has a certain amount stored in it. 2 pounds of compression is 2 pounds of compression. It can't be 4 pounds of compression. It can't be 7 pounds of compression. This is a spring. This is a scale. It's measuring an amount of energy. Momentum is being stored in it. If I push it this way with momentum, I get the same reading that if I let gravity do it here. So gravity creates momentum because it does the same exact thing as a force hitting the spring, puts momentum into the spring, and you can store it because it's not a constant force like gravity, so you have to store it. You have to, whoa, there it is, I locked it. Now I have it in the spring, and now when I release it, I can only release, I put a 1 mass, I'll get a velocity. I put a 2 mass, I'll get half that velocity. I put a 3 mass, I'll get a third that velocity. I put a 4 mass, I'll get a quarter of that velocity. And again, depending on how much friction I end up creating, there'll be a point where, yeah, it's not going to work. It's going to look like no energy is being transferred. Can lead to different amounts of momentum depending on the mass of B. Are you crazy enough to say it doesn't? Yes, of course I am crazy enough to say you have no evidence and otherwise. Now, what you could do is show me a silly cart video, right? The carts with little metal wheels, okay? Little metal wheels on a plastic frame. Now, shouldn't the cart be a metal cart with plastic wheels? Wouldn't that be more sensible? So you have very heavy wheels, very light cart. Okay, now if you use those, then you're not going to see the linear velocity as the total momentum, because a big hunk of the momentum is going to be stored in the rotation of the wheels. And the rotation of the wheels is invisible from our perspective as linear momentum. So we can't see it as a velocity. We can't see rotation as part of the cart's velocity. So that part of the energy isn't revealed until the cart hits something, and then it can give that extra amount of momentum it actually had. So in that case, so if you use heavy carts, you load them up and you have angular rotation, the heavier you make the cart, the less energy is stored in the wheels, right? So the slower the cart goes, the less energy is in the wheels. The faster the cart goes, the more energy is in the wheels, right? So you can just understand that I could do heavy carts, and it could appear like I have more linear momentum, because when I do the lighter cart thing, a big part of the momentum is going to be in the rotation, the very fast spinning of the wheels. So the faster the wheels spin, the more energy they hide. And so then you could get a differential between this. You could use the same spring, and it would appear that you got two different amounts of energy. But it only appears that way because you're using a cart that stores the energy in different places. And at high velocities, it stores the energy in the wheels, and at low velocities, it stores the energy in motion, linear motion. So, fuck you. So what's my response? Are you stupid enough to ask the same question, again, and then to not recognize you just asked the same question over again? Fuckheads. Anyway. All right, so this is a comment by some troll. All right, to steel man, tinfoil hat man your argument. So whatever, I could do without all of that. Anyway, could you just make a counter argument, like where you reference a piece of evidence? Should we assume you don't believe in a massive conspiracy? So understand, there doesn't need to be any massive conspiracy. There's no massive conspiracy that has most of the humans on Earth believing in some wooey, silly, fably, lots of words that start with F. Silly God theory. Okay. It's no conspiracy. Just stupid fuck. That's all you need is stupid fuck. People who just really couldn't care to actually live in the real world. Involving millions of people to hide the shape of the Earth. So they're not hiding it. But clearly, why does the company produce these low-friction carts with this weird configuration of a whole bunch of metal wheels? Why would you do that, right? Is that your definition of low friction, is a bunch of little metal wheels? Why don't you just go with 4 wheels or even 3 wheels? Why not make them very thin and light? I've seen that. And low-energy vehicles use big, light wheels, not little heavy wheels. Rig experiments to validate their theory. So again, I can point to you a bunch of rigged experiments, all right? The Spar lab can't do an experiment rationally or fairly, right? I mean, it did the hammer thing, puts the weight in the wrong place, knocks over a carton, puts the weight in the wrong place. I can show you over and over again how many times they can't measure 4 times the height correctly. The fact that, in 350 years, right, you've been claiming, your people, okay, your clan, has been claiming that 4 pounds dropped 1 foot is the same energy as 1 pound dropped 4 feet, and yet you haven't done the experiment. In fucking 350 years, you couldn't bother. So you don't need to rig an experiment. You just need not to do them. Don't do the experiment, and then you can prove that Jesus is God's son. Because you can just say he walks on water. You don't have to prove that he does. Oh, you're just such a fucking, what a waste of time. So I'll remove that because it's just rubbish. All right, this is some weightlifter guy who showed up saying, hey, older guy, living in the... These are terrible times, I guess he's hit 70. It's just yuck, this getting old thing. So he's clinging to his existence as best he can. I wouldn't, I don't remember the guy, but apparently he's been around a while. And I wouldn't go for this whole eating cow hearts and whatnot kind of stuff to get there, but whatever. I do empathize with this being older thing, and it just is unpleasant. Yeah. Anyway, and then some idiot with this Mathis stuff. Okay, Mathis can't be that well known if this video only has 6,000 views. Well, compared to the usual 150 I get, it's pretty good. But yes, over, how many years that video's been up, he really can't be all that popular because this does show up. This is the kind of crap that, YouTube will link to. It's stuff that isn't my agenda. Somebody else's. It's just really irritating. Oops, I didn't need any of that, whatever that is. Channel customization. I don't think I'll bother with that, thank you. All right, so I could go back to this asshole's first question. So, I mean, it says, thanks for the answer. So you say that momentums in opposite direction must be equal. So, yes, that's what I said. So now he wants to answer the same question again. At least in ideal conditions. I agree. But now there's another question. Well, apparently you don't agree. You think that somehow I can change the momentum that the object has by changing the ratio of the masses. And no, you can't. All right. So here's his original question. If a spring launches two objects in opposite directions, so he doesn't say two equally massed objects, do you think the objects must have equal momentums? So you didn't say two equally massive objects. You said any two objects. And yes, they have equal momentums. And then he sits there and says, are you going to dare to attempt to argue? Are you crazy enough to say it doesn't? Now he's changing his opinion. So anyway. Yeah, I guess that's it. I guess I'll go look and see if there's anything of interest, but, fuck. The internet sucks. Alright, so I did notice Ian Gosling still has this really stupid video up. Okay, so where he makes a really stupid, dumb argument, says things that just aren't true, the whole premise is wrong, the physics is awful, and he just leaves it there. Just really is surprising. Unannotated, didn't change the title, calls it the end of draft science when it's the end of his own credibility. I mean, the error is so bad. It just amazes me. So this is the character of these people. He's not embarrassed by that video. And he's not disturbed that he made such an error. And nothing. Doesn't, just keep on lying. And Despard does the same thing. Leaves videos up where everything he did in the video was wrongly premised. And he just leaves it up as if it's evidence of something. And so you got to argue, is there any point? Is there really any point in interacting with people that dishonest? They won't even fix their own errors. If you call them errors. Like I said, I don't know. There's a point where you say maybe it's not maybe there's not mistakes. It's all part of what they're deliberately trying to do, which is just make distracting noises. So anyway, till the next time and such, and so forth and whatnot.